This is the time series lecture 3 on stationarity, assumptions, and inference for time series models. So stationarity, we use data from the past to predict the future. That's what we're doing with time series. If the future is not like the past, then our predictions will be wrong, and that brings us to stationarity. A time series yt is stationary if its probability distribution does not change over time. In other words, we assume the joint distribution of ys plus 1, ys plus 2, ys plus t does not depend on s regardless of the value of t. Otherwise, yt is non-stationary. This basically says that the future is like the past in probabilistic sense. This makes sense. If you want to predict the future, it better be the case that the future has all the same conditions in the past, or else your model will not do a good job predicting the future. Time series regression with multiple predictor assumptions. So just like we did with multiple regression and ordinary least squares, we're going to have to define our assumptions for time series regression. So for a given model with k additional predictors, or k x variables, where q1 lags of the first predictor are included, so q1 lags of y, and q2 lags of the second predictor are included, and so forth. So we have some y lags and some x1 lags and some xk lags. The expected value of the error term, conditional on everything that's included on the right hand side, that's this stuff here, is equal to 0. In other words, the error term should be uncorrelated with all the included regressors, just like we had before. Assumption number 2, the random variables, yt, and all the included regressors have a stationary distribution. In other words, the distribution of the random variables cannot change over time of the random variables in the model. And b, yt, all the included regressors and the predictor, or the dependent variable, and all of the previous values of the dependent variable and their predictors become independent as j gets large. So as the difference in time periods becomes large. So we're subtracting j time periods. So as we might think of this as 10 years previously. So the variables become independently and identically distributed over some time period within our model. Large outliers are rare, and then there's no perfect multicollinearity. So these two are the same as the regular OLS assumptions. Actually, number 1 is the same as well, but we just have to modify it to include lagged variables. Assumption number 1. This is the mean zero error assumption, or the no correlation between the included regressors and our error term. It's mean zero error given all included regressors and the additional lags. Implies the best forecast regression is the one that's given, the one that we're using. We can't do any better. Assumption number 2 replaces the IID assumption, the independently and identically distributed assumption from the multiple regression models. This means that all data is drawn from a stationary distribution. The distribution of the data generating process does not change over time. If it doesn't hold, the regressors and forecasts can be biased, just like in the multiple regression model. If we have omitted variables, then we get biased coefficient estimates. Same with time series, doesn't change. The forecast can be inefficient, meaning there is a better way to estimate the model with a given data to reduce the mean squared forecasting error. So this says that if we don't have the correct model, our forecasts are inefficient. We can do better. Part B of the assumption says that the random variables must become independently distributed as the amount of time separating them grows. Right? So we know that today's GDP is correlated with yesterday's GDP, but we just want to make sure that it's not correlated with all past values of GDP. At some point, GDP 100 years ago maybe isn't correlated with current period GDP. Forecast uncertainty and forecast intervals. So we've defined how to come up with a forecast But now let's talk about the uncertainty in the forecast and forecast interval. So just like we produce t-stats, confidence intervals, and p-values to determine our statistical uncertainty of our coefficient estimates, we want to produce the same kind of uncertainty measure or statistical certainty around our forecasts. If the errors are normally distributed, then we can produce forecast intervals. The forecasting error consists of two components: the uncertainty arising from the estimating regression coefficients, and then the uncertainty arising from the future unknown values of the error terms. So there's two things happening. There's uncertainty arising from the fact that our regression is not perfect, right? There's always some error involved in our regressions. The betas are not the population betas. That's the first bit here. The second bit is that there's uncertainty in what's going to happen with future random shocks, in this case GDP. So our model is not going to capture a random shock to the economy like a pandemic, for example. That would be contained in future error terms, or UT plus 1, for example. Forecast intervals. Like a confidence interval for forecasts, these contain the forecasted values in 95% of repeated samples. If we assume the errors are normally distributed and the central limit theorem gives us the distribution of the betas being normal, then the forecast is the sum of two independently normally distributed random variables, so the forecast itself is normally distributed. The variance of the forecast is the mean squared forecast error, not the root. The 95% confidence interval is thus y hat t plus 1, conditional on all things that happened in up to period t, plus or minus 1.96. Where do we get the 1.96? From the central limit theorem telling us that the betas are normally distributed, meaning that the forecast itself is normally distributed, times the standard error of the forecast, which is the mean squared forecast error. Forecast intervals are typically presented by, for example, government agencies, the Fed or central banks predicting inflation rates, etc. How many lags should we use? We've introduced the autoregressive distributed lag model. We've said you can include as many lags as you want, but we've also said that we have to get the optimal number of lags. So of course we need some criteria for figuring out what the optimal number of lags is. There's a balance. If there's too many lags, or too few lags, you leave out potentially useful information. Right? If you only use one lag, a lag from 2 periods ago might still contain useful information. If you use too many lags, though, you will be estimating more coefficients than necessary, which introduces additional estimation error. So you want to include the appropriate number of lags. And of course we have statistical tools to help us determine this. The first we'll look at is called the Bayes information criteria, or the BIC. The formula is given at the top of this slide, where SSR P is the sum of the squared residuals from the regression with lags of order P. So P in a first order lag autoregression model would be 1. In a second order with 2 lags P would be equal to 2, and so forth. The BIC estimator of P hat, is the value that minimizes the BIC among all possible choices of lags, numbers of lags. So really what we're doing is we're estimating the autoregressive model with 1 lag, calculating the BIC, estimating with 2 lags, calculating the BIC, calculating with 3 lags, up to the number of lags we want to test, and then looking at the BIC and picking the one that minimizes the BIC. The first term in this equation decreases as you add more terms. The standard, or the sum of squared residuals, is always going to decrease as you add more regressors. But the second term, P plus 1, increases. So this is capturing that trade-off between adding having benefits of adding more regressors in order to get a better prediction. That's the first bit. But then the drawback is that you get more statistical uncertainty when you have more regressors in your model. So that's captured by that bit there. As an example, we'll consider the GDP growth rate regression. The sum of squared residuals decreases as more regressors are added and the R squared increases. You can see that here. They've plotted P going down, so numbers of lags on the in column 1 here. The sum of squared residuals divided by T. This, as you can see, it decreases as you add more lags. This is the right-hand bit of the equation, P plus 1. That's going to increase as you add more lags. And the BIC is minimized right at P equals 2. Also, the R squared is going up as you add more lags. So the best model, according to the BIC, is P equals 2, or 2 lags. So that would be YT equals beta 0 plus beta 1, YT minus 1 plus beta 2, YT minus 2. Another way to look at it is the AIC. An alternative method for determining appropriate lags is given by this formula. The only difference is now we have 2 over t instead of log t over t. Essentially, it's just another way of looking at this. If you aren't really happy with your BIC lag value, or the number of lags the BIC suggests, then the AIC is a reasonable alternative.